When I was thinking about putting together the talk, I found that, there are so many things that I just love about the Bayesian statistics and Bayesian nonparametrics in particular. There's just no way that I could cram them all into an hour, right? And so what I tried to do is tried to think about what I could talk about in an hour that might actually have some sense and have a little bit of meaning. And what I settled on was really trying to focus on 3 examples. Hello? So we'll try to avoid the feedback there. Tried to settle on a few examples of successes of nonparametric Bayesian methods that actually convey just some of the spirit and some of the excitement, I hope, of the methods and what they can do. They're all very simple situations, and they're simple situations not because you can only use the techniques in very simple settings, but rather simple settings and easy situations so you can understand where the benefits come from. And then, of course, there are a million talks at this conference and elsewhere where people use them in much more refined fashions, much more complicated ways, where they see the same benefits. It's just harder to follow what the benefits, where the benefits come from in those situations. So bear with me. Hopefully the examples will not be too simple. And then at the end, hopefully have a little bit of a plea for statistics as an experimental science, and a plea that Bayesians should maybe be a little more experimental than we are when we're thinking about doing our own analyses and about what makes for a good Bayesian analysis versus a poor Bayesian analysis. So here we go. A little bit of an outline. When I talk about the examples here, they're all going to be familiar data sets, ones that everybody in statistics knows. And in some sense, it's one of the great European traditions of things used to be done in Latin here in Europe, right? Everybody spoke Latin, and that was the language of scientific discourse. For statistics, data is what we deal with. And data sets are our lingua franca. There are data sets that everyone should be familiar with. And you say, ooh, the baseball data from Effron and Morris and empirical Bayes, and everybody knows what the data set is. Classic data sets that everybody should know, just so we have a common language and can talk about ideas. Well, before we get to the data, a little bit about Bayesian methods. And there are people far better qualified to talk about these issues than I am, including a couple of the foundational lectures that we've seen already. But when I think about it, there are 2 main routes to Bayesian statistics. And one goes through the development of subjective probability. And for me, it was Savage's book that really just lays things out so beautifully, where he talks about personal probability, starts with the axioms of rational behavior, and says if you start this way, how should you do statistical inference? How do you build models? How do you make decisions? And the consequence is be a Bayesian. And there's just no escape if you accept the axioms of rational behavior. It just proceeds from there. Second approach is purely classical statistics in its origin. You start it out, you lay out a formal decision theory problem. There's nothing Bayesian about it. And you say, how can we think about a good decision rule versus a poor one? You introduce the concept of admissibility. You want to use admissible decision rules. And almost everyone agrees that you should use admissible decision rules. And then you say, what are the set of admissible decision rules? Well, they're Bayes rules or things that are very, very close to Bayes rules in a technical sense. You might use a little bit of an improper prior here or there. And again, if you just don't want to do a bad job, either be a Bayesian or be very, very close to a Bayesian, right on the edge of Bayes. And if you're not, there's something wrong and you're going to do poorly. Now, there are good reasons to be suboptimal, right? To not try to use these admissible rules. But those are special things. They're a fact that you need to compute things quickly. And it's better to have an answer than to have no answer, right? Use an inadmissible rule if you can do that quickly, and the admissible one you can never get to. Wonderful reason. That was Mike Jordan's talk in part the other day. If you look at it and you can't really build a decent model, and you say your model is so deficient in some ways, in that case you might use a rule that formally is inadmissible in some decision problem, because that's not the real world that you're working with. But admissibility gets you there as well. The strength is that we're told that we should be Bayesians. The downside is that neither of these methods by themselves really tell you how to be a Bayesian. That's all extra work which is layered on things, which was part of the joy of listening to Tony O'Hagan's talk on Monday. The first example is going to be Effron and Morris's baseball data. And it's a remarkable example. What I'm going to do is take and tweak it a little bit, but you guys know the setup. Setup is just a classic empirical Bayes problem or compound decision problem. You have a set of parallel problems. Each problem is sort of the same problem, but for a different individual. In this case, we're going to have 18 different individuals. It's an example that was brilliantly chosen every place that baseball is played. So North America, most of Latin America, some places in the Far East, people know about baseball. And they know that if you're going to look at a batting average for people in the major leagues, it's going to be about 0.26 or 0.27 for the fraction of times they get hits. 0.35 would be a really good hitter. Nobody is going to be at 0.4 for a full season. It simply won't happen if they play every day. And so people have all this knowledge just internally stored, and they know what's reasonable and what's not. If you look at 45 at-bats, the beginning of a season for these major league players, the batting averages, some are clearly too high for a season-long batting average. Some are clearly too low. And you know that the individual MLE, player by player, is not going to be a good estimate. Everybody knows this internally. Question is, what else do you do? Goal of this one is to actually forecast the batting average for the remainder of the season. And for this, we just want to think of hits or outs, the two possibilities roughly, as being a success or a failure. We're going to have a basic binomial model for the data that we have. And we can envision the rest of the season as just being a completion of a binomial model with 400 or 500 trials. A lot of trials, but not an infinite number. And we have two main choices. We can deal with this as 18 separate and distinct problems and just build a model for each one to it individually. And there you could use the MLE or you could use something a little bit different. Or we could try to pool information the way that we all know that we should, either with hierarchical Bayes or you could be a heretic and go empirical Bayes. If you do this, Efron and Morris in their early paper just showed the great success. And for this particular picture, there's a blue line at the top, and that is the sum of squared prediction error for remainder of season batting averages, sort of the measure that you set up, if you use player-wise maximum likelihood estimates, just P hat for each of the individual players, PI hat. And you can see it's up at the top of the plot because you do poorly. The blue dot, which is down in the lower left corner, that's what happens if you use an empirical Bayes analysis. It's a little different than what Efron and Morris did in their paper. Here I went with method of moments to estimate hyperparameters of the beta distribution. Then once you have those estimated, treat them as fixed numbers and just feed it back through the problem. And you look at it and you see there's this huge drop from something that's about 0.08, 0.09 for sum of squared prediction error to about a third of that. You reduce it by a third. In fact, it's a bigger reduction than that because there's still variation in how those players performed in the remainder of the season. And so the actual reduction is bigger than a factor of 3 for the reduction. It's amazing, right? And it works brilliantly. Now, what I wanted to do is look a little bit at the notion of admissibility. And so what I did is I've tweaked the data a little bit and adjusted it and just sort of said, well, here are different problems that are still based on the same data, but they're changed a little bit. And as you move from left to right on the plot, what I thought about for the first black line as you move over is you could take the players, and for 17 of the players, you could count the fraction of hits. And for the other player, you just reverse it, and you count the fraction of outs. Right? It moves it from about 1/4 hits to about 3/4, because you're counting the other thing. And so that one player is very different than the others. Right? Stein phenomenon, shrinkage estimation, admissibility still suggests that by shrinking, you should be able to do better. You should dominate the coordinate-wise maximum likelihood estimate. Most of that work is normal theory, but it carries over here. And so what I did was I just picked a player from the 18 at random, did the reversal, fit the model, just ran it through the algorithm to get the estimates, looked at sum of squared prediction error. The black dot is the mean, or reversing over a lot of players. I did a few hundred draws. The upper and bottom edges of the line are the upper and lower quartile for those reversals for the sum of squared prediction error. And you can see that shrinkage is real, right? You still do better even if you reverse one player. But you could reverse 2 players or 3 or 4 or 5 up to 9, and then the picture would look symmetric coming down on the other side because symmetry is the problem. So admissibility is real, right? And if you just use empirical-based techniques and shrinkage estimation, you simply do better here. And that's true. You simply do better even if you're shrinking to completely the wrong point. If you reverse half the players, by the way, you're basically shrinking towards 0.5. Right? Half you're counting outs, half you're counting hits. You shrink everything toward 0.5. Shrinkage still works. Right? And it's amazing that you do better. But when you look at the magnitude of improvement, you can see that the big magnitude of improvement comes from getting a model. And what we're really trying to do with Bayesian statistics is trying to model the data generating mechanism. And if you look at it, that blue dot is a lot lower than any of those black lines. You build a model, if you could capture roughly the right things in that model, you see this huge benefit. Right? Now, this isn't non-parametric Bayes at all so far. Right? There's just a little bit of shrinkage estimation and questions about admissibility. Here's what happens when we think about non-parametric Bayes. You just start asking questions, right? And if the notion is that empirical Bayes is trying to mimic a Bayesian model, and I think that's the best view of empirical Bayes that one can take, the question is, should you really say that all of these players' batting averages follow a beta distribution? What on a mixture of betas or something else? And you ask another question, another question, another question, and you get to this point, which is for Bayesians, oftentimes we want to have what we call full support. Right? If you're thinking about the prior distribution for the probability of heads on a coin, and you're going to flip it, you could say it's just fixed at 0.5, or it's got to be between 0.49 and 5.1 or something like that. And that's fine if you get it right. But if the truth is you get 53% heads, and your prior only assigns mass to 0.49 to 5.1, you pile up at the edge of your prior, and you simply, no matter how much evidence you get, never get to 0.53. Having an open-minded prior in many ways means having full support. And in a problem like this, full support, when we're thinking about these players' potential hitting abilities, is going to be any distribution on the unit interval, right? Any distribution on the unit interval. It's very different than saying it has to be a single beta distribution. So we're naturally pushed in the direction of non-parametric Bayes. And this model is one that's in a wonderful paper by Don Berry and Ron Christensen. It's Ron's master's dissertation, by the way, but it set the tone for a lot of what we have done since in these non-parametric Bayesian methods. And here's what we get. The red dots down at the bottom. Okay? It's just a simple, basic use of the models. It's nothing fancy. It says we're just going to take, write down, in this case, a Dirichlet process for the player's distribution. Simplest kind that you can imagine. The base measure is just Lebesgue measure on the interval 0, 1, uniform for the CDF, a mass of 1. And you just say, let's fit the non-parametric Bayes model with a little bit of MCMC. And it's the same reversals that you see for all these. First, you notice you do a little better than empirical Bayes just by itself. Right? That's probably because the beta distribution is not quite right. And empirical Bayes is always a little bit shady, right, with the double use of the data and such. But the second thing is that when you think about the problem which has been adjusted with the reversals, you still do almost as well as if you'd modeled those reversals. Right? Now, if you knew that it's either the basic problem or the reverse problem, build that into your model. Right? Model whatever you know is real for your data set. But if generically you just know it's a problem where you want to shrink, perhaps not all toward one point, but towards a variety of points, allow yourself the flexibility to pick up the patterns that really are there in the data. And you find out that a simple model like this, you can do far, far better than any other technique I know across this whole range of problems. And of course, what we want to do is do well not only for an individual problem, but we want to do well for whole collections of problems. So we develop techniques that work for one problem and the next as we turn to them. This one just amazed me when I saw it. But I really get this huge, huge benefit just for moving from parametric Bayes or empirical Bayes to non-parametric Bayes. And it comes almost for free. This is an easy problem. Computations work well in it, in everything. Enormous difference. And again, when you look at the magnitude of improvement, it's almost as good as modeling in that pure sense. And that's a big surprise. A couple of comments. There are a lot of people in the classical statistics community who like to talk about shrinkage. And they say shrinkage is a wonderful thing and it's going to fix everything, right? Nowadays they use a different code word. It's regularization, right? And those are pretty good code words, right? But that's not really what matters. What matters is building models so you can capture the right data generating mechanism. If you can build a model that captures some of that and you can do Bayes, integrate instead of maximize, you actually do far, far, far better, right? It's a coherent worldview and it simply works. If you are going to go with regularization, take and read a couple of Chris Hans's papers about Bayesian versions of the lasso, where integration is just better than maximization. It's so convincing when you read them. You'll never go back and just regularize stuff. But you guys wouldn't anyway, right? Because you wouldn't be here if you were maximizers, right? No, but actually you are maximizers. You're utility maximizers, right? And that's really what optimization is all about, right? Maximization of utility. Hey, so what underlies this? What underlies this is a model called the Dirichlet process, and it's kind of the granddaddy of nonparametric Bayesian models. Nonparametric in the sense of placing models in spaces of distributions. Developed in the early 1970s by Ferguson in a wonderful paper that is tough to read, but still a wonderful paper. Has antecedents that go back at least to the 50s, maybe earlier. And he said there are two big properties that you need to have for nonparametric Bayes to be successful. The first is you want to develop a prior distribution that has large support, or ideally full support in some sense, in an appropriate space. Appropriate space might be the unit interval, if we're thinking about this problem where the theta i's are between 0 and 1. It might be the real line, it might be the positive half line, it might be RP. It's whatever space is reasonable for the sort of problem that you're interested in. These theta i's have to live somewhere. Find the space where they live, have full support on that space. Technical issues about what full support means. You can measure support in different ways. At the time, he was thinking, I think, about just weak support, traditional things for distributions, but there are refinements since then that a lot of you in the audience know so much about. Second thing, ability to perform updates. You have to go from your prior distribution to a posterior distribution if you get data. In the 1970s, it was super conjugate. You had to be able to do it with pencil and paper, essentially. Nowadays, if you can do it with MCMC, you can do it with MCMC, and we can effectively update our prior distribution, get to a posterior. There's still simulation inaccuracy in there. That's okay. You get a good posterior, you do very well predictively. If you prefer variational approximation or something like that, another way to quickly fit the models, that's a great way to go too. But we have to be able to perform the update somehow for things to be useful. Dirichlet process, constructed in lots of different ways, and I'm not going to step through those constructions here, but every construction gets you, number one, to the same mathematical object in the end. I mean, they all produce the same mathematical object, which is neat. It means that you can use the different constructions for different views on that object, which has turned out to be useful for developing sampling strategies and things like that, for Markov chain Monte Carlo. But it also means that you can take the different routes to the Dirichlet process and you can relax them a little bit and create other processes. Right? So the limit of Dirichlet multinomial problems is kind of a first pass that has antecedents that go way back. Instead of a Dirichlet multinomial, you could take a product beta multinomial setup, you can get the Polya trees, and you can get mixtures of Polya trees if you go that route. If you like gamma processes, and you're going to rescale so it becomes a probability measure, you could pop something in that's different than a gamma process, rescale that, and you can have normalized random measures. You can look at an ERN scheme, and you can tinker with the ERN scheme and come up with Pitt-Manure processes. You can look at stick breaking, and you can use a different version of stick breaking and come up with different processes. There's a lot of flexibility here. And so you can create things that are not the Dirichlet process. The others are very valuable processes. You might construct them in particular ways to achieve particular purposes. And there are a lot of talks here that are actually using other constructions for particular purposes. So Lee Ma, I think, is going to talk about testing for finding differences among portions of distributions rather than the whole distribution and such. A lot of good uses of them. One construction that makes it easy to see what they're about is just a stick-breaking construction due to Sethuraman and Tewari. The distributions that you get from the Dirichlet process, if you draw one from this prior process, are discrete. And when you draw a discrete distribution, there are two things that matter. You have to know where you have lumps of mass, where the atoms are. Those are the theta I stars. And the recipe for that is simple with the Dirichlet process. They're IID draws from some distribution F0. Just a random sample from F0. It'll be a countable discrete distribution, so you have to draw lots of them, like an infinite number. The second thing is you need to know about the weights. And the weights all come from these stick-breaking variants, these VIs. And those are just a random sample of betas. They're an IID sample. They all come from a beta distribution with parameter 1 and m for the mass of the Dirichlet process. Once you have those variants, then you construct the probabilities. First probability is just V1, that first break of the stick. Second probability, you say, of the mass that remains, 1 minus V1, you're going to take a fraction V2. V2 times 1 minus V1. You just keep breaking off pieces of your stick like that until, well, it's never all gone, but in the limit it's all gone. And use those to construct the weights. Once you have that, you've got the locations where you have mass, and you've got the amounts of mass. You have a probability distribution, and then you go from there. Strongly connected, by the way, to the pull-urine scheme. Jeff Miller has a nice paper out, and Jalen Lee has some nice work on how the connection goes. Problem with the Dirichlet process. Those distributions are discrete. And most of what we do in statistics uses continuous distributions rather than discrete distributions. If you're going to think about a regression model, usually the errors follow a continuous distribution, maybe normals, for example. And what we like to do is come up with a continuous version. How do we get there? You take the Dirichlet process and you smooth it out. And the way you smooth it is just by smoothing it with the kernel. So you look at it and you draw a distribution F from the Dirichlet process. It's this ugly, nasty, discrete thing, countable number of atoms. And you say we can smooth it, maybe with a normal kernel or some other kernel of your choosing. After you smooth it, you now have a mixture of normals or a mixture of something. But you have something that's continuous. And with that continuity, then you can work with all the usual tools. Early work, Antoniak did his dissertation. Ferguson was his advisor back in the early 70s. He laid all this out in a wonderful, wonderful paper. Didn't catch on for a while. And the reason it didn't is that nobody could do the computation. It was simply too hard if you had more than like 4 or 5 observations. Oh, even in the 70s, people had more than 4 or 5 observations. Yes. Yeah. You know, we look at it and you have smooth versions of the Dirichlet process. You can smooth them in a lot of different ways, of course. What I've written down here is one of the standard ones that works pretty well. But in fact, you can smooth in many other ways. Nowadays, it's wonderful because this is just a component that you can plug in as a piece of a hierarchical model. Once you plug that component in, you now have something that no longer says it's a particular parametric form, but you have this component that allows extra flexibility. And if you want the flexibility in that component of your model, this is one way to do it, and it works awfully well. Computation. Computation was the big hurdle throughout the 70s and 80s, and in fact, you know, in the late 80s, almost nobody was working on nonparametric Bayes. There was a wonderful tradition in Italy, but other parts of the world it had kind of fallen away for the most part. Mike Escobar in his PhD dissertation, which was 1988, in fact, worked with John Hartigan and used Markov chain Monte Carlo techniques to fit the models. Remarkably enough, it's kind of a parallel development with the Gibbs sampler of these techniques. For Mike, it was specific to the mixture of Dirichlet process kind of models, but very effective. Alan and Adrian, of course, applied it to everything in the world, right? And we all know it as Gibbs sampling and such now. But remarkable, there was parallel development. There are a lot of advances from the basic algorithm. Right? The advances matter. Algorithmic refinements, it improves mixing, it improves convergence toward the limiting distribution. So if you get into this and you actually use the techniques, go with the more modern algorithms. They really do work better, and it's worthwhile. They'll let you stretch to problems that have less conjugacy and things like that as well. Other approximations. There's variational approximations. There are some other approximations out there. Those are worth using, right? They tend to be fast. They've been developed so they can handle bigger data sets. They can scale up in a sense. There's a work going on in MCMC to scale those up as well. It's very good work. One of the uses of these is just to fit the models. Another use is to do exploratory analyses. And one of the things that we always hope when we try out models is to see this huge success, right? And Ed George talked about it in his talk, where he said he made a plot, and he just saw when he saw that plot that this was going to be big, that his analysis compared to the standard that people have been using was simply going to be more successful. To do that, you might look at a lot of models. You need to look through them quickly, rather than taking a long time to look at one. Approximations and shortcuts in computation as part of good exploratory data analysis are a wonderful thing to do. Should be used more in the Bayes community than they are, in fact. If you want to just stick with that for your final analysis, great. If not, go back and do a later, more careful analysis after you pick the rough form for the model. But the differences for these models can be so big that even in approximation, you see there's huge benefit. Once you have that huge benefit, you pursue it and you refine your model a little bit more. If you want to try them out, DP package, Alejandro Hara and crew have a nice way to do it. It's also very fast because it's coded, I think it's in Fortran that underlies it. So you get very, very rapid coding and things like that. Ooh, what are we going for time here? All my clocks disappeared over here. There's one over there. Oh, too bad for you guys. The fire alarm might cut us off, in fact, yeah. So two big ways to work with nonparametric Bayes models, right? And the first approach is density estimation. And Mike West was very influential in kind of building this view and putting it out there in the early days. Peter Muller and others as well at Duke. And part of the view is just that you could view the entire world as density estimation, right? And if you come up with a really good density estimate for explanatory variables, I'll call those X, and the response or responses, we'll call those Y. If you have that joint distribution for X's and Y's, explanatories and responses, you can extract any conditionals you want. And so you can extract the conditional distribution for Y given X, what we think of as regression. If you have that joint model, you can get everything from it. It's actually philosophically a very pleasing, very sound kind of view. And it works awfully well for modest dimension problems. I mean, you can really pick up some nice regression surfaces that you might not think of otherwise. The downside is that when you get to very high dimensional problems, you get hit with the curse of dimensionality. And density estimation is simply a hard problem if you have 20 or 30 or 100 dimensions, no matter how you slice it. It's just a tough problem. So it's a nice strategy. It's very effective for some problems. But if there are problems where you feel you need to add a little structure, the density estimation by itself worldview starts to break down. And so what a lot of the modeling has gravitated towards is sort of structured modeling, where you're going to lay out a general structure for your model. It'll be much like a standard hierarchical model. Then you're going to pick particular components, and you're going to build nonparametric Bayes versions for those components. So you might look at it and you might say, I'm thinking of a regression problem. I know I'm going to condition on the X's for my final inference. What I really need is a component that lets me model the distribution of Y given X. And then you get to model that however you want. You get to pick out a mean function. You get to pick out variance functions if you want to have scale changes as well. But you can also think about the distribution of the residuals, distribution of the errors from that Y given X model. And if you think about distribution for the errors, you might go with something like the errors are IID, just the standard kind of regression models we write down where we tend to say they're normally distributed. But alternatively, what you could do is you could think about a collection of distributions. And if you think about the collection of distributions, and it's just, say, simple linear regression, you can just slide that covariate along from low values up to high values. And if you want your error distribution to be the same for all values of X, go with the Dirichlet process, mixture of Dirichlet processes sort of model. If instead what you'd like to do is see that error distribution change or evolve in X, and David Dunson calls this density regression, very nice kind of language to capture it. What you'd like to do very often, because when you look at the data, you see that the distribution of the errors of residuals is simply different at one covariate value compared to another covariate value. You'd like to build models that allow you to change that in a nice continuum if X can lie along a continuum. And so how do you do it? You start with one of the basic constructions and you just tweak it and change it a little bit. And that location, instead of just being the draw from a normal distribution, that would be the same for all values of covariate if you're going to start with the Dirichlet process and smooth it. You just replace it. You say, let's make that a stochastic process, indexed by the covariate. A Gaussian process, we all know about those. So instead of picking a single normal variate, you draw the path of a stochastic process, and that's going to be one of the locations. You pick one value for your covariate, it's a normal. You pick another value for a covariate, it's a normal, random samples of them, an infinite collection of paths of stochastic processes, all independent, and you just build your model in that fashion. You can do the same sorts of things for the stick-breaking variants, and you can either keep them constant or you can have stochastic processes that go along there. Stick-breaking variants, by the way, you can actually add a lump of mass at 0 to those beta 1m's, and then you can have covariates that kind of wink in. You can have atoms of mass that kind of wink in and out of existence as you take and you change your covariates. That is sometimes useful for modeling. But the point is that we have very structured ways to change these distributions and create not a single distribution, but a whole family of distributions. And if it's indexed by a covariate, it doesn't have to be a one-dimensional covariate. We have Gaussian processes and stochastic processes that have essentially arbitrary index sets. So you can have multi-dimensional covariates and you just have a recipe for construction. It can be time, it can be space. It can be time and space and covariance. We just have recipes for building these collections of distributions. And of course, if you know how you built the distribution, you know that the paths of those stochastic processes inherit properties from the stochastic processes themselves. And if you just have a countable mixture of stochastic processes, or you have something that's not quite a countable mixture if you let these weights change as well, you know that you can just pass properties from one to the other. And you can get things like continuity if you want to build a continuity in. You can get different amounts of differentiability if you want to build that in. Really what you end up with at some level is a distribution valued stochastic process with index set of your changing. And when you do that, of course, you have these creatures. The big use of them is to use them in a coherent and a structured fashion when you're building models. If you're going to do this, by the way, you also need the data to support the model. Don't build a crazy model if you have like the 4 or 5 observations, because then your model is going wild, right? And you don't have the data to support it and inform the model. Modeling. Enormous amount of modeling done in the nonparametric Bayes world. Wonderful book which came out recently. Peter Muller, Fernando Quintana, Alejandro Jara, and Tim Hansen. It's a thin little volume, but there's just a lot of wisdom in it. So grab it, read it, and you'll find out all sorts of great things about modeling. Really wonderful, wonderful stuff. But nonparametric Bayes is now used all over the place, as is seen, in a sense, by the success of the nonparametric Bayes section of ISBA. And if you see the talks that are given here, you'll see there's a strong flavor of this in many, many of them. I'm going to go quick over the next couple of examples, because otherwise I'll get the hook from Alejandro. I'll get the hook soon. So here we go. Classic data set, log body weight, log brain weight for a bunch of species of mammals. There are no dinosaurs like we saw in a talk yesterday because they're extinct. And so we don't have a pocket of unusual observations here. If you look at this, right-hand plot is actually a picture of standardized residuals just from a basic least squares fit, right? Most people look at it and say, well, normality looks so good, right? But I look at it and say, not really. Residuals at the top are about +3 for standardized residuals. Ones on the bottom, they get down to about -1.5, except for the water opossum that has an unusually small brain, given its body size for some reason. When I look at it, I see a little bit of a hook in the middle. There's almost a bend, right? And what that corresponds to is a little bit of skewness. But it's a modest amount of skewness in this case, right? It's not the kind of thing that just leaps out at your eye and you say, I have to do something that replaces normal errors. Here it's, passable to do a normal analysis. What I have here, and you'll see that part of the plot is perhaps with my luggage, is you see that there are a fit of 2 different models, and one is just a normal theory regression model. That's the curve on the bottom. These are log marginal likelihoods indexed by the slope parameter, which is what people are interested in with this data set. The top one, you see for the big hook up the top, actually has to do with fitting a model, which is just a simple linear regression model for the basic structure, and it's just IID errors from a mixture of Dirichlet processes for the other model. Computation here really nails it down, and so these are not the standard MCMC for computation, but really trying to evaluate log marginal likelihoods at all those places. And there are little error bars on there if you could actually see them. There are 2 things to notice. Number one, the Dirichlet process model is just pumped up about 4 in terms of log likelihood scale, so it's noticeably better fit in one case. And the second thing you notice is it's a sharper bend for the mixture of Dirichlet processes model. That sharper bend, sharper pattern for the log marginal likelihood translates to a sharper likelihood, which then translates to a sharper, tighter posterior distribution. This is something we often see in nonparametric Bayes models when we fit them. And it seems paradoxical at first, and people were a little skeptical when we first started seeing this, because we knew that at the time computation was far from perfect. And the question was, is this just bad MCMC, or is there a real effect here? It's a real effect. I mean, our computation is good enough now. We know it's real, and we can see it repeated many times. Question is, why does it appear? Because it doesn't always appear. Sometimes that nonparametric model has a flatter posterior, sometimes it's sharper. There was some work I did with former student Subha Guha, and now down at University of Florida. And we really took a look at this and tried to explain the behavior. And the conclusion that we came to is that, in fact, the distribution of the covariate has a big impact on how this is going to turn out. And the reason it has a big impact is you can imagine not sort of the best fitting value or the true value of beta, but if you get that value wrong a little bit, what happens? If you have the wrong slope for your model, and you've got a normally distributed covariate, where you're going to be off by, aggregated across the different possible values of the covariate, is something that looks like an extra normal variant. And you're really going to have a convolution of the actual error distribution with this normal distribution when you look at the errors in their aggregate. That becomes more normal than the original non-normal error distribution. And it's that effect which is sharpening the posterior. If you had, for example, a non-normally distributed covariate, you could actually see the opposite effect. And we can actually show that in some cases. So it's kind of interesting. We actually see a little bit about why this behavior happens. And you pursue it more and you say, suppose I was just a parametric guy and I wanted to do these normal theory models always. If I had a non-normally distributed covariate and you get the wrong slope in there, you're convolving that normal error distribution with something non-normal. There's a question of whether your parametric analysis is artificially coming up with too sharp a posterior distribution. At some level, you've said, when you got the wrong fit, I'm still going to force those errors to be normal. Although when you convolve the normal errors with this non-normal covariate distribution of the wrong beta, in fact, it should be non-normal. Right? I would argue that the baseline analysis you should do here is one that allows flexibility in the error distribution. It's tied a little bit, in a sense, to versions of least squares, where there are versions of least squares that make no reference to normal distributions. It's just least squares, sort of moment-constraint kinds of models. And at some level, this a non-parametric Bayes regression with mixture of Dirichlet processes for the errors is addressing that same problem. And it does have some appeal. It also departs from pure least squares. And so I think this one actually kind of gets standard errors right, in a sense. Here, there's a dual to a model like this. A dual structure here is to write out the model that where you actually write down kind of the thetas that go along with each individual case. There's no star on the thetas here. In this case, you might view this as a version of the mixed model. It's a little easier to see if you have some replication, so I've written it with replication in this slide. But again, we come back to the same theme of full support is a good thing for a Bayesian prior distribution. If you have fixed effects are just numbers. Full support, if you have two of them, is going to be R2. If you're going to talk about random effects, the support for random effects, because a random effect is conceptualized as a draw from a distribution, it's the space of all distributions on the relevant space. And it suggests that for random effects, you should use a non-parametric Bayes component. And in fact, the many, many successful uses of non-parametric Bayes, where you're really writing down non-parametric Bayes for random effects, conventional parametric models for fixed effects. And as a recipe, that would be the first thing I would try. It really does work well, time and time again. Third data set has to do with outliers and kind of how to handle outliers. And when we think about outliers, there are a couple of very classic examples of how to deal with outliers. You go back, the first two papers by Box and Chow in the 1960s, in fact, where they said if you're worried about outliers in your data set and what they might do to a Bayesian analysis, just work with a thick-tailed likelihood. Right? And thick-tailed likelihood actually does a remarkably good job of handling outliers. It effectively discounts them or can discard them if they're big outliers and your tails are thick enough. And there are a lot of details for how that works. If you're using the thick-tailed likelihood only to handle outliers, but it's not a likelihood of belief, the subjective Bayes argument loses its force. You're not saying you believe this is how the data is produced, but you're rather saying, my data have some problems, so I'll just write down a thick-tailed likelihood model so that they sweep the problems under the rug, and I can still do well for the center of a distribution. It's not a bad thing to do, but you are doing something which is different than saying, I'm trying to capture the distribution that generates the data. Another tradition is to use two-component mixtures. There's a good component and a bad component. The bad component has an inflated variance, a lot like the thick-tailed likelihoods. But again, you're sort of trying to do maybe a little more modeling in a case like that. When I've tried it, it rarely matches diagnostic plots. Errors when they pop into your data sets and are bad, a lot of times they're just not symmetric. They're not nicely distributed. They're just these ugly creatures that just appear and pollute your data set. But if you don't write down likelihoods you believe, you're not really being fully Bayesian. Right? So third approach is a little more modern. And this says that what you can do is you can just try a technique, and there are going to be talks on Thursday on this, and there's just sort of growing work on it, which is to really pursue a strategy where you'll write down a much more flexible model, write down a model that's in a much bigger space. Then after you write down that much bigger model, what you're going to do is you're going to take and you're going to shuffle something away from the modeling and into the inference to actually handle how you deal with deficiencies in your model, in this case, outliers. And so what Juhi Lee and I did a few years ago was to try this out for outliers. And what we did is we kind of drew a page from Huber's old book on robust statistics, purely classical stuff. And yet there's this tradition in robust statistics of developing robust estimators. And a robust estimator, you're going to replace, say, a log likelihood that you would try to maximize for estimation with a criterion function. And so a criterion function here might be this function rho that's just down toward the middle of the page in blue. And what you're going to do is something that maybe looks like a normal likelihood, nice and quadratic at the beginning, and then you linearize it. This is what Huber does for one of his. And if you do that, then you're going to downweight the tails, right? And you end up with something that people call the Huber estimator. You can get the median out, you can get the mean out if you do this. It's all a question of how you specify a rho. And for robust estimation, usually you're working with empirical data, and you take and you maximize and you say, this gives me an estimate of a parameter. The theory, of course, is much deeper than that, and it's in the book. What you could do is you could think about an arbitrary distribution F. It doesn't have to be an empirical distribution at all. It's just a probability distribution. And by virtue of hitting it or crossing it with one of these loss functions, this rho function, what you really do is you define a parameter. Right? And so what we're going to do is we're going to think about fitting models very flexibly, and then for the inference portion of things, using things that are not just automatically running to the mean, but thinking about how we summarize a distribution. It's a very flexible distribution. Right? If you're working with normals, the mean, the median, anything symmetric, you get the same point estimate. You turn the distribution into the same parameter. For these more complicated ones, you get something different. So this is an example of speed of light data from Newcomb. It's a classic standard old data set. 2 outliers, 64 observations that look pretty good. Question about those outliers. Now people know a lot about the speed of light that they didn't know when the experiment is done. 2 models. One is just a straight up normal theory model. Second one is a mixture of Dirichlet processes model. There's a split or partitioning of variances due to Jim Griffin that produces better density estimates, and so we've used that here. Parameterization matters and thinking hard about them. And here's the results. Fit the normal theory model, that's the black line. This is the posterior distribution for the center of the distribution, the mean. For the red one, we fit the more flexible model, and we summarize it with the mean. We have ways of drawing essentially all of F. And so we can compute the mean for each MCMC draw of F. This is a kernel density estimate of all those means, a few thousand of them drawn together. And you can see they're different. When you fit the more flexible model, even if you're summarizing with the mean, they're different. If you go to a summary that's a little more robust and it's going to discount the tails of a distribution, this is Huber's summary, here's what you get. Completely different, right? The outliers are both on one side. They're way down on the bottom. And those get discounted because they're in that tail by Huber's estimate. If you go with the median, you get something that is indistinguishable from Huber's estimate. And by the way, if you're fitting that normal theory model, this was the Huber estimate and the median under the normal theory model. The center of a normal distribution is the center of the normal distribution. So by choice of inference function, you can actually get something very different. And the interesting thing here is that if we were to take and use the thick-tailed likelihood, here a T with 4 degrees of freedom, that Box and Chow would suggest, this is what you get. I mean, even that model says the center is way up there on the right-hand side. And that agrees more with modern views about the speed of light, by the way. And so what we have is a case where instead of just saying we're concerned about outliers, we use a thick-tailed likelihood, use it coarsely, fit the model and see where the center is, because it's designed to pin down the center, that kind of analysis. What we can do is we can fit a much more flexible model, work with one of these inference functions that maps a distribution, a very complex, rich distribution, a draw of F, into a number, which is going to be our parameter. And we can look at that parameter, measure of the center. And we find out that we get, in a sense, to reduce both bias and variance. And if you can reduce both, you just have a winning combination. Right? Really powerful stuff for the summarization. This strategy in general, I think, is a big one. It's got a lot of room to grow. There is work which is not only non-parametric Bayes, but people are just plucking off one example after another. Some very nice work by Carlos Carvalho and Han, where they take and they fit very high dimensional regression models and then do posterior summarization. It's the same idea. Shuffle things from the modeling part into the inference part. And for Bayesians, we can do this. If you're not a Bayesian, if you're a classical statistician, in a bit of a caricature, classical statisticians are just constructing an estimator. They don't have the freedom to think both about the modeling and then estimation as a completely separate inference part of the problem. We have that flexibility and we should use it. Can pay some very real dividends. Simple low-dimensional parametric models, you don't tend to get very much. High-dimensional models, non-parametric models, you get a huge amount. Second bit, and this I'll be quick on. There is a big difference between these models and traditional parametric models. And the big divide here, I think, is that for the parametric Bayes models, oftentimes you can elicit an enormous amount, and you should do that if you're going to do a good Bayesian analysis. For the non-parametric models, they're infinite dimensional. And that means that at some point, try as hard as you may to do elicitation, you have to write down a rule. And you say the remainder of my distribution is specified by this rule, right? And whether you call the rule objective Bayes or something else, if you have an infinite number of parameters, at some point there's going to be a rule that just operates. Whether that's good or bad, we don't really know, right? We have some evidence that says that it seems to be good for certain structures and certain inference problems because it seems to have worked. But it's nothing like a theory that really tells us why it has to be good. It would be wonderful if we could stretch and get there. But it is different because it doesn't really capture your beliefs. There's a rule that appears in there somewhere. As soon as you have that rule, then you lose the full force of the arguments that make Bayes so good, right? Because it's not really subjective probability in its fullest sense. And when you do that, you might have to depart some other places as well. So with Xinyi Xu, a colleague at Ohio State, there are questions about doing things for Bayes factors, for example, that lead to posterior probabilities for model comparison. And if you were to look at the prior distributions and take draws from the prior for these non-parametric Bayes model and ask, where do you put mass? Some of the mass is put in crazy places. And it's the rule that's putting that mass in crazy places. When you put mass off in some bizarre place, it couldn't possibly reflect data that you're going to see, simply because it's a rule and you can work with the procedures. That's part of what you get for your Bayes factor. Those stuff, it gets zeroed out by the likelihood, right? Much better is to do a substantial update, which is not minimal training sample size or anything like that before you start computing Bayes factors, but something that's an update so that your posterior looks like it's sensible. Then start the model comparison, the computing Bayes factors. And that seems to work pretty well. There's a question of where do you start computing. There's some arbitrariness there, but you need to do something. Better to do something that seems sensible than do nothing at all. Would be my view on that. I guess almost out of time here. If you do pursue this course where some aspects of the problem you think you can do well, others you don't really believe because that's sort of the tail end of your model that is perhaps not too supported, you might consider using the portions that you think you've gotten right or approximately right for your updates. So there's Bayesian restricted likelihood that I worked on with John Lewis, who is here, and Yoon Lee. Some Bayesian robust empirical likelihood. There was a talk yesterday on that, Catherine Forbes and a student of hers. There is approaches where you take summary statistics, rely on asymptotic normality, and pursue that. Chris Holmes, Stephen Walker, and others. Laura Ventura, Walter Racugno, many, many more. There's the ABC work that people are doing. Real questions about what to do when you do have these very complex problems and you don't actually believe all aspects of your model. That's tough, because as soon as we take that step, we kind of break the complete coherence of Bayes, which is one of the most beautiful things about it. The last little bit, work with Mario Perugian, a former student of ours. Mario is one of the best modelers you'll ever find. We took a look at things, and I'll just show you a couple slides. Top little bit is humans doing modeling. Sum of squared error, this is the ozone data set. It's legitimate. This is modeling part of the data out of sample. Do better than any of the classical things that you just could think about. BART is extraordinarily good, as many of us have come to find out. If we look at classification, high ozone, low ozone days, the humans did a little bit better than BART. And there may be something about humans trying to build coherent models that will allow you to make inferences for many problems simultaneously, whereas BART has a particular focus. And it does very well on that. It does well on associated things as well, but maybe perhaps doesn't have the stretch of things. We also looked at individual analysts who tend to overstate how accurate they are. We heard in Phil David's talk about the importance of calibration. What we found, and this was partly us, is that each of us was a little too optimistic. If you looked at our sort of interior assessment model fit versus what the world was telling us, each of us individually was a little too optimistic. This should be 90% coverage here. If you combined us, we ended up getting rid of some of that optimism. So multiple analysts, having different people look at data and kind of all participate seems to be something good. But the last little bit at the end is, it would be wonderful if people figure out how to do Bayesian statistics better. There's a long tradition of this for decades. It's a tradition that should not be sacrificed simply because we can do fancy computational stuff and deal with one data set or another very, very quickly. The foundational stuff that we heard talks about the last couple of days is so important. I think everybody should read it, study it, learn about it, because I think it matters when you're constructing more complicated models too. Thank you for your attention.